Okay, so we're going to go over the bronze solutions and then we're going to go over some general contest tips and then go into the silver solutions. So our first presenter is going to be Ryan Fu with bronze number one.
Is the screen share working for everyone? All right.
I
So
can
for
see it.
problem, okay. So for problem one, it's called FEB, and there's a lot of flavor text in the problem, but essentially what it says is we have a string consisting of B, E, and F, and then F's can either be a B or an E, and every time we have an occurrence of B, B, or EE inside our string, the excitement level of our string increments by one, and we want to find the distinct excitement levels there are, and we want to find exactly what those excitement levels are. So when looking at a problem, it's usually a good idea to start with the samples first. And then for the first sample, which is 4, and then B, E, E, F, we see that our F can become either an E or a B. And in the former case, you'll have an excitement level of 2. And in the latter, you'll have an excitement level of 1. And then this motivates us for a for a O of n times 2 to the n solution, where we can essentially brute force where if every F is a B or an E, and then we check the excitement level. But obviously this won't run in time since n is like 10 to the 5. So with that, we'll continue searching for a solution and go to the next sample case. This one, it's FEB, FEB, and FEB. And we see that for the first F, if it becomes a B, then that'll like increase our excitement level by 0. And then if it becomes an E, it'll increase our excitement level by 1. And for the other two Fs, we also notice that if they're either B or E, they'll both increase the excitement level by exactly 1. So this gives us like two more observations. The first of which is that excitement level for like different consecutive runs or like contiguous substrings of Fs is independent from the other ones. So it's like no matter what the value of the first F returns, like that won't affect the return value of like other uh, contiguous Fs. And then our second observation is that this is like is that the answer or the possibilities for F will always be deterministic given the amount of F's in starting and ending character. And these two observations will motivate us to like find the uh, to solve for when there's only like one contiguous run of F's. And then after like messing around, we see that there are in fact 4 cases for this. First is when you have like a same character and then a run of F's and then another of the same character. So like B, F, 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 and then B, or like E, F, 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 E. And then on paper, we see that if like we have K F's and if K is even, then we can have like 1, 3, all the way to K plus 1 are possible. And if K is odd, then we have 0, 2, all the way to K plus 1. And we can just do this by observation. But if you wanted to prove this, then it's really easy with induction. And then we can do pretty much the same thing for one character and then a run of F's and then a different character. Um, Either E, F, 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 B, or like B, F, 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 E. And then we'll have like a different observation here, specifically when it's even 0 to all the way to K are possible, and when it's odd, 1, 3 to K are possible. And then apart from this, we still have some edge cases where where first of all we either have like no characters or one character adjacent to our run of Fs. Where this one character, it's not hard to see that it's 0 to K are all possible. And then for no characters, boarding it, this case is also really trivial, and it's 0 to K minus 1 are all possible. So now we can like calculate what like the answer I guess would be for each subsegment of F's in our string, but we still need to like combine those answers. So the way to do that is with this observation, where we see that unless like S starts or ends with an F, we have for any segment of F's, we start from 0 or 1 and then increment by 2. And then if you look at like this slide right here, we see that this is in fact the case where you're always starting from like 1 or 0, and then you're going up by 2. And this allows us to really easily, if Google Slides will load here, um, what allows us to like combine these results. Like for example, in this, we know that this BB will always return a 1, and then this FFF will be a 1 or 3, and this FFF will be a 0, 2, or 4. So then, like, so you're gonna start with at least 2 because this is 1 and this is at least 1. But then for each thing you increment, you'll always be incrementing by 2, and you can increment exactly 3 times. So then that will return answers of 2, 4, 6, or 8. However, there's still the case where our string does start or end with f, but in the previous case, we could only return like only even or odd numbers. But if we start or end with some run of f, because these aren't limited to a certain parity, we can like attain all numbers now from the min to the max, because we can just add 1 to like to the parity we're limited to previously. So for the previous example, let's say if we just add another 3 f's to the top, then now we can obtain everything from 2 to 11. So this is our pseudocode essentially. So first we just like take all the inputs, and then we find like excluding all the starting or ending f's, we can classify all the contiguous segments of f into the 4 previously defined categories. Then for like b or e's, we can always add 1 to the min variable, since like we know that those will always like add excitement 1. And then we find like the min and max excitement for like if all the f's are like one character or another, and then from this information we're able to solve the problem. This was my code for the problem, if it'll load. And it's commented here, and I can send a link to this if you guys want, where like you're first getting the inputs, then you're doing the calculations, and at the end you're outputting stuff. Are there any questions right now? I'll take that as a no. And then let's move on to problem 2, which is Mu language. This problem is like pretty long, but as a summary, you're given n words, and these are classified into nouns, transitive words, intransitive verbs, and conjunctions. And you're also given C commas and P periods. And there are 2 ways to make sentences out of these. The first of which is to have a noun, an intransitive verb, and the second of which is a noun, a transitive verb, and then more nouns. But you have to have commas separating those nouns. And then 2 sentences can be joined with like a conjunction or a period, but you can't join 3 consecutive sentences with 2 conjunctions, and we want to find a paragraph with the most amount of words. So first, if Google Slides will load, we'll define some variables. So if we let T1 be the number of sentences of type 1, and T2 be the number of sentences of type 2, and NN be the number of nouns, and T be the number of transitive verbs, etc., we know that the sentences of type 1 are limited by the number of the intransitive verbs, and the second types of sentence is limited by the number of transitive verbs, which is where we get the first 2 inequalities. And then we also get that since we need to have at least 2 nouns in every transitive, in every type 2 sentence, and at least 1 in every type 1 sentence, that's where you get the third inequality. So that's all very well. So since n is less than 1000, we know that T1 and T2 are less than 1000, and that since the USACO judge usually allows for like 2 EA operations, if we can find whether each value of T1 or T2 works for in like O of 1, then we can compute the result pretty quickly. So this is what our pseudocode uh, will look like so far. And like so far, we're literally only checking if we have the required amount of nouns and verbs to satisfy our values of T1 and T2. So then, like, now that we have this approach, let's consider what happens when we like fix T1 and T2, and we've already ensured there's enough verbs and nouns. At this point, like to have a valid paragraph, we'll still need to connect sentences together with either periods or conjunctions. But then of the two, we'll prefer conjunctions since that's just another word that we want to use, and we want to optimize the amount of words. To satisfy like the constraints of the problems, that we can't have like infinite conjunctions. We'll use min of the number of conjunctions as well as like half the total amount of sentences that we're going to use because we need to like have the other half with periods in between. And then one more way to use words that we've kind of forgotten until now is with the type 2 sentences where we can use more nouns than just two. And then without affecting our answer and simply and to like simply implement this easier, we'll just like tack on as many nouns as we can to the end of our first type 2 sentence, like if we even have like a type 2 sentence. And since we have C commas, we've already used T1 plus 2 times T2 of those nouns. The amount of like extra nouns we have. Oh, sorry. The slide is wrong. But the amount of extra nouns we can add is the min of n minus like T1 plus 2 times T2 in C because it's limited by either the amount of commas or the amount of nouns we have left. So summing everything up, we'll have that amount of words. For implementation details, there's two. So first, apart from like a variable to count our best number of words, we should also like keep variables to store the values of T1 and T2, as well as like other variables that like return the best amount of words. So that way we won't have to like keep computing the paragraph over and over again, which will make our program run faster. And also, in programs like these, where like you have a lot of input output, it's a good idea to unsync the input and output so it can like so your program can run faster, I guess. And this is your pseudocode essentially, and like for conciseness, we don't check for edge cases here, but this is like an actual implementation. And again, I'll send it to you guys if you want. So yeah, that's bronze 1 and bronze 2.
Okay. Thank you, Ryan. My name is Ryan, and I'll be going over Palm 3 from this year's Bronze US Open. Let me just. Can you guys see that? Okay. So. Okay, so wait, actually, we should plug over to Palm first. Yeah. So essentially, what's happening is that we have Phototrons and cows are having a dance in which they just like which at every point they just move one shift over. And okay, wait, let me just see this. So at every timestamp, all of Phototrons active cows will shift over one position in front of their line, and the active positions in the end will switch one ahead in the array. And if that doesn't make sense, in the sample input, our initial array is 0, 1, 2, 3, 4, and our active positions are 0, 2, 3. And in our first timestamp, we're going to rotate 0 to 3. So the cows at 0, 2, and 3, they will shift to the active position 1 ahead of it. So the cow at position 0 is going to go to position 2, and then cow position 2 is going to go to position 3, and 3 is going to go to 0. So after that, our order is going to look like this. And then afterwards, our active positions is also going to switch. So all of this, we're just going to add 1, and if we ever go over the bounds of the array, we're going to circle back to the beginning. So you can think of it as like a circle, and we're just going to be wrapping around every time. Okay, so for the first key observation of this problem, we're given that the active positions are always going to be in sorted order. So 0 is always going to move to 2, and that means that this 0 is going to catch up again to this 2. So we know that whenever a cow gets moved, it's going to get moved by some exact distance every single time. So if we moved cow 0 by 2, then it's going to move by 2 again when we reach it later on. Because since it's in sort of order, if we keep shifting forward, then we're never going to hit that index again by another index that isn't the index that we jumped from. That doesn't really make sense. Let me draw it out. Okay, so essentially we have like 0, 1, 2, 3, 4. Wait, can you guys see that? Let me share. Can you guys see that? I hope so. And we have our active positions at 0, 2, and 3, for example. And so if this 0 jumps to 2, and we just keep shifting these active positions on and on, like that, then we actually won't reach this 2 again with any of these cows in front, because they already moved in front. And if they wrap around, it's going to go back to the beginning. And so whenever we hit this cow again and move this again, so let's just say at this point, this is 1 ahead of time. So it's going to be 0, 2, 3. So when we hit this again, it's going to be with the same active position that we hit it with at this beginning. So when we hit this again, we're going to be jumping by 2, just like we did from here. And with that, we can basically see that every cow will always jump a specific amount. And so we can process these independently. Okay. So with this, we can just calculate, okay, we're at this cow and we want to go forward in time by step. So we have to check when's the active position that we're going to catch up to and how many times will we jump. And that should be pretty easy as long as we just keep an array and process them in order. And now we have another problem, which is if we jump over the length of the array, how can we guarantee that we're going to get the correct active position? And we're just going to use modulo. So if we have position 1 and we jump by n, then we're going to go back to 0, right? So we can just take whatever position that we jumped by and just add our jumps times the length of the jump and then take it modulo n. And this will give us the correct position for our current cow. Does that make sense? Okay, if so, then I'll just be going over the solution code. I'll also drop the link in chat, so if you guys want to follow along, you can. Right now, we just have C++ code. Okay, so basically, we're just going to be reading in active values and adding n to the end, because whenever we jump forward, we just also want to keep track of all the numbers after the last active cow, because those will also be bumped by the one behind it. And this is really just for implementation purposes. If you really wanted to, you could just go do it at the end, but it just makes it a little bit easier. So we're going to go through all of the active positions and go through every single position we can use active positions. And you might think that this block of code is going to be like n squared, But remember that these active positions are all between 0 and n. So the total number of iterations that we go over between these two for loops is going to be just O of n. Okay, so this is going to be the time it takes for the active position that's going to hit it to reach it. So if we were at some position, let's say 0, 1, 2, and we have an active position at 0 and 4, then we want to know, first of all, are we gonna ever move at all? Because if t just equals 1, then we're just gonna switch 4 and 0, and we're gonna stop. So we're gonna see, all right, how long will it take for this active position to reach us? And is this larger than t? So this is gonna be our exit time. And then if our exit time is greater than or equal to 0, then we jump at least once. So I'm gonna take this exit time and divide it by the difference that we move every time and add 1. And so our ending reach is just going to be our current position plus the difference that we jump by every time times the number of times that it gets hit by it. And we're just going to take this module n, like we said in this slideshow. Does that make sense? Okay. If you look back at this and you don't really get it, you can always message me in chat and I'll respond. Okay. And then if we don't ever get hit by an active position, then we didn't move at all. So we're just going to set our new position to just the same position. And then the answer to our position that we eventually move to at the end is going to be our current number. What is times hit? Times hit is the number that times hit is the number of times that the active position behind us hits us. So like if it was 0, 1, 2, and then we're currently on this second position, and our active position is 0, then and t equals 2, then our times hit, or t equals 3, then times hit equals 1. Sorry if my handwriting's messy. I'm drawing on a mouse right now. Because we're going to shift this once, and then we're going to move over to here. We're going to shift this over once, and then we're going to move I'm going to move over here. And so after 3 time movements, then we're going to reach this thing. And what this formula basically is when t gets really big, like when it reaches like 100 so, we're going to circle around and hit this 2 many times with our active position. And we're going to jump ahead some amount if we had multiple active positions. And so we're just going to say if t equals 100, and then the active position behind us is at this position, then how many times will we be jumping ahead to the next active position? Does that make sense? Okay, great. So yeah, we're just gonna print out the answer here. This sort of notation here where I say space new line and I do like index, this is basically just saying, oh, if I equals n-1, how and I and line, otherwise how and I and just space. That's basically what this is. This is just a string and we're indexing it with a boolean, but that's essentially what it means. Okay, if this code makes sense, then I'll hand it off to the next person, who I think is Kevin, or wait, I can check.
No, I believe this is for Rohan to cover.
Yeah.
Yes. Okay, Rohan. My bad.
Okay, can everyone see my screen? I'll assume yes. All right, so I'll be going over silver problem 1, which is milk sum. So in summary, Farmer John has like Farmer John has N cows which produce milk at rates A1 to AN, and so they're hooked up to a milking machine, and essentially, Farmer John's gonna stop the cows, one per second, and after K seconds, the cow that he stops will be producing K times A of I milk. So if he stops the first cow, let's say cow X, then like that cow's gonna contribute A of X units, and so on. So the second cow would contribute 2 A of Y, third cow would contribute 3. All right, can you hear me now?
Yeah, we can
Okay,
hear you.
all right. So someone's saying that my volume was not high. Maybe try increasing your computer output volume. Okay, I'll continue. So the third cow is going to contribute 3 AZ total units and so on. So we want to find the maximum possible amount of milk Farmer John can collect. And so we have Q queries, and after each of them, we're going to update the value of A of I to J, and we want to calculate a new value for this maximum output. So first, we're going to look at the sample case. So first, let's say the original one. So we have 5 cows, 1, 10, 4, 2, and 6, and so we want to pick like the cows that are producing the least first, because the cows that are producing more would be more beneficial to like unhook later. So this one would produce, we would choose this one for time 1, so we would get 1 unit of milk. We would hook this one up second, so we would get 4 units of milk, 2 times 2. Then we would do this one, so it's 4 times 3, which is 12. And then the 6 would be 24. And then finally, the 10 would be 50. Okay, so, and then if we add these up, we'll get 91, I think, units of milk. And 99, sorry. And if we keep doing this, 91, yeah, the original answer was right. Okay, so we have 91 units of milk originally. And after the first update, we're changing the value of the second cow to 1. So this 10 is gone, and we have 1. So now we see that it's not as beneficial to keep the 10 at the end, because now we're only producing 5 units of milk instead of 50. So now we have to, instead of making this this is as the last one, we're going to make this as the first or second. It doesn't matter because these are both equal. So this one will now produce 2. And then the third cow would now be the 2 cow. So that would be 6. And then the 4 would be the 4th cow. So it would be 16. And then the 6 would be the last cow. So we'd instead produce 30. So this leads us to a pretty this leads us to our naive solution, which is highlighted here. So after every query, we're going to change the value of the ith cow to j, and then sort the array to find like the order that we want to unhook them, and then take the sum. And this would be O of nq log n. And unfortunately, this is too slow to pass because n and q are both 1.5 E5, and that would not pass in 4 seconds for C++ and 8 seconds for Python. So first, let's try to speed up the solution, and I'm gonna break it up into 2 parts. So the first part is removing the existing cow. So instead of thinking about it changing the cow's value, I'm thinking about it in a way that's like remove the cow that we originally had and add a new cow. So let's just say in our original in the sample we had 1, 10, 2, 4, 6. So and the answer for this one was 91. So now we see that when we remove the 10, we're actually, since this is the last value, we just get rid of the 10 and nothing else. So we're subtracting 5 times 10. Subtract 5 times 10. So this is gone. And we have 1, 2, 4, 6 with an output of 41. So now the second part is going to be adding the new value. And the new value is equal to 1. So let's just say we're inserting a 1 here. And now we see that the cows in these 3 positions, so 2, 4, and 6, they originally produced, this one was unhooked second, this one was originally unhooked third, and this one was originally unhooked fourth. And now by adding this 1, we're chaining this cow's unhooked value to 3, this cow's unhooked value to 4, and this cow's unhooked value to 5. So essentially, we're adding 2 plus 4 plus 6, which is 12. And then furthermore, when we add the cow position, this cow with value 1, and in the second position for unhooking, we also add 1 times 2. So this is 55, and that's the answer for the test case, or for that query. So now we're going to figure out how to do this more generally. So first, let's handle the idea of removing the cow that was originally there. So first, we sort the array, like the original one that we're given, and for each cow, we assign it like an unhooking value. So for our original array of 1, 10, 2, 4, 6, the unhooking value of 1 is 1, the unhooking value of 2 is 2, then the 4 is 3, the 6 is 4, and the 10 is 5. So now we know how much each value actually contributes to the total sum. And when we're unhooking a certain cow, so let's say cow number 10, we're removing 50 units, so we'll get 41 left. So the other thing that we need to handle is that, let's just say this was not 5. Let's say we were unhooking the 4th cow instead. So let me do this. Yeah, so let's say we are unhooking the 4th cow, or the cow with value 4. So now we see that we lose 12, so 91 minus 12, but we also see that the cows that with unhooking value 4 and 5, now instead of going times 4 and times 5, this actually becomes 3, and this becomes 4. So we're subtracting 10 plus 6. And the way that we can compute this in all of one time, like the value after removing the original cow, is by making a prefix sum array. So we originally sorted the cow, so we have 1, 2, 4, 6, 10. And if we're removing the cow at position 4, then we also subtract 6 plus 10. So we take it's actually not a prefix sum array. I guess you could do a suffix sums, like do it from backwards, but it doesn't matter. We can just take the entire sum of the array, subtracting from the first 3 values. And so we first subtract 4 times 3, and then we subtract the prefix sum, the last 2 values, which will be 10 plus 6. So we figured out how to remove the cow. So now we have to handle adding the new cow back. And this is the harder part of the problem, in my opinion. So inserting the new value, and first we need to find the position that we're going to insert it at. So we had 1, 2, 4, 6, 10. And I'm just going to remove 6 for now because 10 is at the end, and I would like to deal with the middle cases instead. So let's say we remove 6, and we're adding a value 1. So first we have to figure out when we want to unhook it. So let's just say the new value is 1, and we want to unhook it as early as possible. So if we chuck everything into a set, then we can use a lower bound function in C++, and I think Java also has it, I'm not sure. So we can chuck this new value 1 right here. And we can compute the position that it's going to be at. So this is going to be position 2. And then we can add 2 times 1 back into our answer. So we had the original, we handled removing the cow in the original position, and now we compute the new position of the cow that we're adding. So this is going to add back 1 times 2. And we see that we decremented 10 over here. Or not, sorry, we decremented 10, and this is shifted back 1. So now all of these get pushed back 1 more. So we're adding this back, we're adding this back, and then we're moving the 10 back. And so we're adding back 2 plus 4 plus 10, which is 16. And then, so this is the first part, that's adding 16. And we can also compute this using the exact same strategy as before by using the prefix sum array that we computed for the first part of the problem. But we need to be a bit careful here. So if we do use the prefix sum array and we add back 2, 4, 6, 10, then we're actually adding back the 6, and we're not supposed to do this. So if the new value of the cow, so this is 2, if 2 is less than 6, then we have to add the prefix sum array back, but then we have to subtract 6 because we're counting it 1 extra time. And then that's the solution, because once we subtract the 6, or sorry, this would be 22 minus 6. So 1 times 2 plus 22 minus 6. And in the other case, let's just say we're had 1, 2, 4, 6, 10. And we're adding back an 8 in exchange for the 6. So we have an 8. Then we see that the 6 in the prefix sum after 10, so over here, we never add the 6 back. So we don't need to worry about subtracting it when we take this the sum of the last few elements. And so my implementation is here. I will send it in the chat. Okay, so the first thing, I take the input, which is integer n, and I create a set. So one thing to note is that sets can only store distinct values. So I made a set of pairs instead, and in the first value in the pair, so I stored the value of the cow, and in the second I stored the index. So if our thing was like 1, 2, 10, 6, 4, then we would store, like, the set would be 1, 0, 2, 1, 10, 2, 4, 3, and then 6, 4. And then I made a vector which stored how much they produce and then the index. So I'll explain what the index one does. And I took the inputs of how much they produce, I inserted everything in the set. And so what the index thing does is this is essentially the unhooking value of each one. And I computed this by first, when I checked everything to its set, it ordered it for me or sorted it for me. And then I made a new variable called index that started at 1. And then we iterate through the elements of all the cows. And then we increment in the index one by one every time. And we store that the index, or the unhooking value of that certain cow, is going to be the in minus 1. And then also I created a prefix sum array by incrementing x dot first, which was how much it produces. So that was the first part of just like setting everything up. So now we have the query, which is the main part of the problem. So the first thing I did is I erased the original cow, and then I made the new variable called ants, which was equal to the original value. So then I first decremented it by the prefix sum, which was like the entire thing, which is prefix n, and then I subtracted prefix of index of in, which is equal to like the first up to the unhooking value of the index that we're changing, and then I subtracted the actual cow itself, which was going to be like the unhooking value times how much it produced. So there's one extra thing to handle here, is that when the cow that we're adding is at the end of the array, there isn't a prefix to add. So if it's at the end, we simply just add n times j, because if it's the highest value, then we want to unhook it last. So that'll be n times the new value, which is j. And otherwise, we go into the actual solution. So I used the lower bound function as described earlier to find the pair that was right above the new value that we're adding. And then I added back the prefix, and then I added back the new cow's value. So instead of like subtracting the production of the original cow, in the case that the new cow that we're adding was less, so I just compared the pairs. So if the original cow is greater than or equal to the first cow, then I added back j minus how much the original cow produced, and then I outputted the answer. And make sure you don't forget the last part, which is inserting the original cow back into the set. So does anyone have any questions on my implementation or the solution? All right, I guess the next person, I think Kevin can take over.
Yep, that's me. Let me share my screen real quick. Don't worry about the bubbles on the sides. That's just a little feature of the browser I use. Anyways, field day. That's the problem I'm gonna do. it's quite a simple problem, and I'll admit I actually spent an hour coding the wrong problem. We have 100,000 teams, which are really bit strings. Each has 18 characters max, and for each team, we want to calculate the maximum number of differences for that team across all the others. And I saw this differences, and I thought XOR, and I spent an hour making a program to code the maximum XOR you could get for each team, and I looked at the sample case and I was like, oh, that was an hour of my time wasted. But anyways, it's quite a simple problem, but it's a bit difficult to actually figure out. So if you'll notice, the maximum length is 18, and that's really short. It's to the point where 2 to the n actually works. So how can we exploit that? So actually I lied. 2 to the 18, it only works if that's your overall complexity. If we tried every possible difference in characters, it's like if we had a certain team, it's like, so what if does a team with 1 difference exist? Does a team with 2 differences exist? If we tried all of those possible differences, that would result in us checking 2 to the 18 other possible bit strings, and 100k times that. I don't think it definitely doesn't fly. So actually, quick prerequisite check. How many people here are familiar with bit operations? How many silver people? Are all the silver kids here familiar with bit operations? If you're not, send a message in the chat, and I'll try to give a crash course on it real quick. All right, cool. Seems like everyone's good with. Oh. All right. I'm gonna have to give a bit of a crash course later. How about meet in the middle? Is anyone? By the way, I don't write the problems. I'm just presenting the solution, just making sure how many of you people know. Meet in the middle right now is in the gold module, I believe. But every year, BenQ decides to push down the divisions of topics. Yeah, robot instructions. That was a previous problem. That was also meet in the middle. Yeah, I guess Brian or Ben just likes to push them down. Anyways, moving on. But not to worry, because I have a specific slide that gives us a quick meet in the middle crash course. I'm so good at this. Anyways, CSCS has a really good demo problem. It's called, well, meet in the middle. Obviously, I don't know. It couldn't be more obvious, but we have n equals 40 numbers, and that's a very weird bound. So just keep that in mind. And how we have an array of n numbers, and we want the number of subsets of the numbers that give us a sum of x. So notice that if we, okay, actually there's a part of the slides that, yeah, iterating, the only possible, if you think about this for like 30 minutes, it's like, the only possible solution you have would be like iterating through all the subsets like a pleb. But that would be 2 to the 40, and that's more than a couple billion. I think it reaches trillions, not sure. But it's way too bad. It's bad, basically. So, like the slides say, we split it in half. And we have the two meet in the middle. Now I know you guys might be a little confused by what meet in the middle actually means. So let's just, let me use the sample case as a quick demo. So 1, 2, 3, 2, that is our initial array, and we want the numbers to sum to 5. We want a subset to sum to 5. Now, how can we, now we want to iterate over all subsets without the awful time complexity. Or what we really want is just a way to calculate stuff over all subsets. We don't actually have to, this initial statement was a bit misleading. We just want a way to calculate the value of something over all subsets. And the way we do that is that by splitting this, split 1, 1, 2, 3, 2. By the way, can you guys see the text I'm writing? Oh no. Oh, sorry. Let me reshare. All right. Yeah, we have 1, 2, 3, 2. That's our sample case. We want it to sum to 5. We want to iterate overall subsets without the awful time complexity. And what we really want is a way to calculate stuff overall subsets without the performance concerns. So to do that, we split 1, 2, 3, 2 into 1, 2, and 3, 2. And let's calculate over these subsets. Now, quick question. Hypothetically, given that n is 40, if we just split it in half, like 20, 20, and we calculate it for each of those, that would work, right? Just say I wanted to calculate it for each of these subsets. Do you guys think that'll fly? So let me ask again. Hypothetically, if n is 40, right? If I split that 40 into arrays of 20 and 20, would calculating the sum of each of those 2 to the 20 subsets, would that fit? Would that? Yeah, 2 to the 20. Right now that's 2 to the 20 with 2 to the 20, which is 1 million. That should fly for n equals 40. Now, here's where the magic of meet in the middle happens. So let me just 1, 2 gives you the sums of let's see here 0, 1, 2, and 3. By the way, tell me if anything's unclear in this explanation. And 3, 2 gives us the sums of 0, 2, 3, and 5. If we store these values in a hash app, in a frequency table, because we actually want duplicate values. If 2 different subsets sum to the same thing, we want to keep track of each of the 2, because the problem asks for the total number of distinct subsets overall that sum to a certain number. So yeah, we can't just keep track, use a hash set for each of these. We need a frequency table, but that doesn't impact the complexity. It actually results in the same complexity. We can do an O of 1, a constant time matchup between the possible sums of these subsets. Don't worry, this is going to go back to the problem, I swear. So we have sums of 0. So I'm going to go through this subset and try to match it up with elements in these subsets. 0, we get 5. 1, no match. 2 goes to 3. 3 goes to 2. So our answer is 3. Yeah, that's how it is. That's how you do it. Let me save these notes. I might want to share these sometime. Anyway, so that's how you do this meet in the middle. Hold on, let me check if is the actual answer 3. Yeah, the actual answer is 3. I'll send that image later, just right after I finish this lecture. So now we go back to our regularly scheduled solution. Let's use the sample case. Y'all are probably familiar with that. I'm staring at it for 4 hours. Who knows how long you guys spent on that problem? Let me just pull up the sample case again. Yep, that's the sample case we know and love. We have let's see here. By the way, let me see, what did I represent G as? I represent G. Okay, G's are 1 and H's are 0. So you guys are, so that's what bit op sample case. Let me convert this to a bit op to binary strings. 1000 and 01001. All right, that is our sample case. Yeah, but we all know that feeling of just like all that effort and for nothing. So meet in the middle. we're gonna do what we did for the CSES problem. We're gonna split these into two halves. In my solution, these are called half one and half two. I do this for all my MITM problems. By the way, these actually don't have to be halves. They just have to be two parts, so that like calculating each of the halves is manageable. So so if it's an odd number, you can just split it into 2 and 3, 3 and 2, or even hypothetically, some people actually just split it using the upper bound, calculate it using the upper bounds. Like some people, if they have a length 13, they'd split into 9 and 4 because that's still a manageable complexity. But I digress. Oh, that's for some web dev stuff I'm learning. Don't mind that. Anyways, for each team, we go through all the possible half ones that they can be matched up with. So let's see here. Let's take our sample case 1 0 1 1 0. We split it into half one is now 10 and half two is now 110. This is a binary string, of course. And now what we want to do is go through all possible half ones this can be matched with. I know this was in the slides as well, but I just want to make this extra clear. So this possible half ones, we have 0 0 0 0 1 1 0 1 1, and immediately half of these actually don't occur. Literally don't occur in our team composition. So let's just let me just mark these in red. Let's see here, which ones don't exist. 1 1. Doesn't exist. Doesn't exist. Now what we move on to is given our current binary string and the half one we match up with, what half two should we do? Now, raw iterating naively over all half twos, that would be, we can't naively iterate over all half twos. That'd just give us 100k times 2 to the 9 times 2 to the 9 equals 100k times 2 to the 18 equals bad. So what we do is we actually do a bit of pre-calculation for the second half. So we pre-calculate the best half two, which removes that extra 2 to the 9 factor. So what the heck? All right. So if you don't know what I'm talking about, actually here's now the current team and the other team's half one are set. So like I said, the only thing that's variable is the other team's half point. And like I said, we can't add another loop, so we do a bit of pre-calculation. And here's actually when I was doing this on my own whiteboard, this is what I wrote down. So so if right here you can see like what an example of what I mean. So like this is our current bit string that we're trying to match up with, that we're calculating the answer for. And here we have set our half one. And here is the pre-calculation loop that I tried to do. So for all possible half ones, and yeah, I have a whiteboard. And for all other teams that have that half one, and for all the possible half twos, so given this half one that I circled in blue and this other half two that I circled in blue, what's the best half two you can do? And that gives us, and this entire pre-calculation process is another 10 to the 5 times 2 to the 9, which is manageable. So by taking this out, we have reached just O of n times 2 to the O of n. Let's see here. What's our final complexity? N times 2 to the c divided by 2. That's our final time complexity. And let me go over the code first, and then you guys can ask me questions about whatever it may be that confuses you about this problem. So let's see here. Yeah, sorry, no Python today. Python is just bad for problems like these. Look, I love Python too, but like sometimes you just have to let it go. So here we read input. I calculate the half one size and the half two size here. Here, I split the pair into ints. I split the teams into a pair, like to like split them in half. So valid half twos represents all half twos with the given half. So you give it a half one, and it'll spit back a set, giving back all the half twos. It's like let me go back to the string here. All right, let me just make some code examples here. Valid half twos. And again, I'm using the sample case. Valid half twos 10. If you give it the half one here, it would give you would equal 1, 110, and 0. Hold on, I think I might have missed a 0 here. Apologies for that. Well, so this is what valid half twos does. Now here we read input. I feel like this should be pretty simple. This bitwise operation, all you have to know is that it takes the first half two size bits, and this takes the anything past half two size bits. So I do a bit of there's actually 2 rounds of pre-calculation here. One is just for calculating the differences between all possible teams, and that's just 2 to the 9 times 2 to the 18 total, worst case scenario, and that is manageable. I use a built-in pop count, which counts the number of bits that are set in an integer. I think it's G++ exclusive. I don't really like using it, but it's necessary in this case. And T1 XOR T2 gives, that gives you back a bit string that's just an integer. If T1 and T2 are set, if T1 and T2 are different, the bit in the remaining value is set. Otherwise, it's 0. So that's why I use that's what this does. It calculates the number of differences between T1 and T2. And here is the pre-calculation that I talked about. So given the current half one and the other half two, what's the best we can do? And I declare vector here. And for all possible half ones, for all possible half twos, you'll notice that I set the default value in the vector to be -1. That means that like you literally can't do anything. It's impossible to get this half one, and you'll see why I use that later. And for each of the half ones, and for each of the half twos, and for each of the teams that have that half two, we do a standard maximum calculation. We update it with the team difference between this half two, the half two we have, and the other team of the half two with half two. And here is where we finally calculate our final answer for each half one, half two, and teams. We go through all possible other half ones and use our pre-calculation. But you'll see this is where the -1 comes back. If the value is -1, meaning that this is impossible, we skip updating it. If you remove this, USACO will throw an error. This will give a wrong answer because it'll just look for the best half one, even though it literally might not exist in our team list. And here we just iterate. This is the sum of the half one difference. This is the sum of the half two difference. We update the maximum. We push it back to our answer array, and we print out our answer array here. All right. Does anyone have any questions? This was a big problem. I don't know why they thought it was a good idea to put this in Solver, to be honest. All right. Yeah, this problem should be gold. Are there BFS? Is there a DP solve? Well, it would take too long if I presented every possible solution. There's probably like 10 ways to solve just this one problem, to solve any problem really. But anyways, if that is all the questions you guys have, then I will be handing this off to the next person. Oh, Ryan, it's Ryan again. Ryan, you're back up.
Hello. Okay. So speaking of interesting problems with Solver, this is another interesting problem solver. Pareidolia, I think I said it correct. But essentially, what it is that it's a phenomenon where you see familiar patterns in images where it doesn't exist. And so Parmesan is always like with Bessie. And so whenever he looks at strings, he always sees Bessie. And given some string, he'll see the number of Bessies as the number of subsequences, which has Bessie. So if we had some string like this one here, he'll see Bessie in here. So we remove Q and Y here. And you also see Bessie in this part where we remove Z. And so we'll talk about this vision that Parmesan has as B of S, where it represents the maximum number of repeated copies of Bessie in a string S if he deletes one or more characters from it. So for example, here we could delete Q, delete I and Y, delete X, delete Z, and delete B to get 2. And so instead of just calculating B of S, we want to figure out B of S, the sum of all BFS. The sum of all B of S's over the entire string of S. Wait. The sum of B of S's over every single substring of S. My bad. So example for here, we have Bessie, and then we have 1 here, and 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 we have another 1 here. And so you'll see that this gets very cancerous very quickly, because if we were to just like count BFS for like the entire string or just one part of string, then we might need to recalculate for a different substring. So we have to be a little smart about how we calculate this sum. So example for this one, the answer is 28. I'm not going to go over all the sums because this is really bad. But for a lot of people in contests, a lot of people went for the inputs 3 to 5, where the string has length of at most 5,000. This essentially lets you get a partial where you just go for all n squared substrings. So that was a more simplified problem. Okay. So pareidolia. The first observation that we have to make is that if we already have 1 Bessie and we add an extra letter to it, then we get 1 more. So if we already have some prefix of a string which has some number of Bessies, when we go over to the next letter, then we get another copy of those Bessies. Does that make sense? I don't even know. But I will draw it out again. So if we have like Bessie, 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 then this is going to be, then B of this entire string S is going to be 3. Oh my god, what's happening? B of S equals 3, right? And so if, for example, we added an X to the end of this, then when we take this entire string again, then we also get B of S equals 3. And so this kind of motivates us to think, oh, if we just iterate along the prefix of this string, then we just iterate along the prefix of the string, then maybe we can just add on the number of Bessies that we've already seen to our answer. And that's basically correct. What extension is that for VS Code? It's Scala or something. I don't know what it's called. But if you just look up Excalidraw, then you'll probably find it. I'll send you a message later on the name of that. Okay, so basically this just says, oh, maybe we should just iterate over the prefix of the string. And our second observation is that now that we have a method for calculating our answer correctly, then how do we calculate the number of Bessies in our array for some prefix and update the new number of finished Bessies as we go on? So what you note is that if we have a subsequence with a prefix of Bessie or completed, actually just this is good really. If we currently have an array with a prefix of Bessie already completed, then all those prefixes get extended if we reach the next letter. So this basically means if we have some B X E X X, then if we encounter this S here, then we can reference this back to E because when we had this E, we're looking for an S. So maybe this kind of motivates us, or this when I was working on this problem, this is what I was thinking. Now that we're currently at E, maybe we need to be looking for the next letter, which is S. And so let's store like a next array where next of I represents, let me just type this out, represents the number of prefixes that need letter I. And I is like less than or equal to 5 because Bessie is 6 letters long. Yeah, so we say, oh, if we have a letter, we're going to go to the next one. And so here's an example of what we might do. We see a B, and then we go here and find an E, and now we're looking for S. And so this is kind of the situation that we have as we go over the entire array. Of course, in this case, we only have one Bessie, but if we have multiple, then we'll just store that count in our array. And yeah, that is basically all you need for the solution. So, yeah. So here is the code. I'll send a link in chat. But basically, if any of you are in gold, then this is basically like elementary DP. Or even if you're in silver, you might want to look into like the introduction to DP module for gold. You don't need to solve any of the problems. But this the way that we solve this problem is very similar to like a one-dimensional DP, where we're like, oh, in this case, we have our DP transition from like if we reach the if position, if we reach the next letter, then we want to transition from all prefixes which already have the previous letter. Yeah. It was very questionable when I was looking at this as well, because I was like, why would they add like a DP like problem to silver? But I guess it's a sign that silver is getting harder. So you should look into next division a little bit, since just to prepare. Okay, so this is the code. We're going to be looking. So next is just going to store the number of substrings which need index I. So for example, if we had BES, BES, then next of Dewey, next for Dewey is going to be 1. And this is because the number of things, like if we label this string Bessie, they will just label it like 0, 1, 2, 3 as we go. Then we have one substring which needs index 3. And so that's why we have this. And so we're going to just first of all we'll try to start something in I. So if we start at I, then we need a letter B. And then if this character is not the end of the string, or if the current letter exists in Bessie, then then we need to look for the number of substrings which have this previously. So if we have like X, T, B, then if this current letter is in the string Bessie, they want to look for a number of substrings which need this letter. And so we're just going to transition this over to the next one. So we have like B, E, S, S. If we have like B, S, S, then we have I. So currently our DPOA is going to be like, we need number of things that need 0, 1, 2, 3, 4. The number of letters that need 4 is currently 1. And now that we found an I, now need of 4 is going to be 0, and need of 5 is going to be 1. Because now we just need E. And we no longer need an I because we already found an I. And this is kind of motivated by that whenever we already have a prefix, we want to try to complete it. And we don't just want to leave them running. Because if we have VESS, and we have an I, and we have an X, and we have another I, and then an E. Really, we don't want to take the second I. Because even though in this entire string it doesn't matter, if you have an E before this, then we always want to take this earlier I. And if you have an E after another I, it still doesn't make sense to take this I. Because if we take this I instead, then we still get Vessi. So whenever we have a chance to continue our current substring, we should just take it. And then we have C1 and C2 here because Bessie has duplicate letters. Because Bessie, there are 2 S's and there are 2 E's, unfortunately. So we have to transition from both. Because if you have an E, then everything that's at Bessie without the Bessie without the E, we can transition. And for everything with just a B, then we can also transition. And so we're going to I'm just going to move on. So C1 plus 1 mod 6. We're going to add all the things that need it. And then we're going to add C1 equals 0. And then if C1 doesn't equal C2, meaning that we are on E or S, then we're also going to transition that. Okay. And then 1 is basically going to be the number of finished substrings. Because if you remember from observation 1, if we already have a completed Bessie and we continue on, then we also get 1 more of that Bessie. So if we finish this substring with an E, then we're just going to say, we're just going to add that to a 1. And we're just going to store the number of finished Bessies. Yeah, okay. And naturally, if we have C1 equals 5 and we finish the E, then we're going to be looking for another 0. So that's why we take mod 6 here. Because after we finish a substring, we're going to need to start another substring. Okay, does that make sense? Cool. I'm going to assume that that's a yes. But at the end, I'm just going to print yes, and that is basically going to be a problem. Does that make sense? Or is there any part that you want to review? No. Yeah, I was talking to a lot of my friends in the silver division, and they said like some of the implementations were like really long. So hopefully this implementation is a little bit nicer to look at. Okay, cool. If that's it, then I guess we're done. Cool. Okay, I'll pass it back to Melody now.
Okay, so I hope that helped. Before we end, we have like a quick discussion just in general, since this is the US Open, the last contest of the year. I was wondering if anyone had any questions on like, what should I do to study for next year? How can I pass to higher divisions? Or what should I do in this time where I have a couple months between this contest and the next contest? What should I do? So does anyone have any specific questions? And then do any of the presenters have any advice from like competing this year? Okay, well, in general, how to pass is just do more questions. I think we've seen a trend with, if you've seen some of these solutions where a lot of algorithms from higher divisions are like showing up. So from the USACO guide, I think we'll be moving down some of the topics in gold to silver. And then also a lot of the gold topics have been present. So like a question may not be intended to have like DFS, but if you know it, it's really useful. So like taking a brief look at the gold algorithms especially is very useful because for some reason these solutions are more present. Why did BFS move to silver in the USACO guide? Because I think we found that it was more relevant for silver competitors to learn BFS because a lot of questions, again, can be solved with these algorithms, even if they weren't intended to be the solution. Okay, any more general questions, thoughts? Should I do all the problems in the USACO guide? I think in general, it really depends on the time you have, since obviously being a middle school, high school student, you do get busy, you don't have time to do questions. It is really helpful to do just the start questions or just the first couple questions. If you have no more questions, you do it. But if you can't, like if you don't have the time, just do the start questions and then go down the modules for the algorithms you don't know a lot. So if you have the time, it's better to do all of them, but if not, look like target where your weaknesses are.